In the following video, we will discuss one method of finding the acceleration of the center of mass of a yo-yo. The yo-yo will be released from rest, as you can see in the following clip. Okay, so now we are going to find out the acceleration of the yo-yo. Over here, I've drawn a free body diagram of the yo-yo detailing the forces that are being enacted upon the yo-yo as it travels downward. Here's the tension of the string and the weight of the yo-yo itself. Also illustrated here, I have the outer radius, which I'll call big R, and then the inner radius, of which the string is wrapped around, and that we will call small r. And in this case, big R is 2 times small r. Now over here we have our mass acceleration diagram, which details our mass times acceleration that is coming from the center of gravity. And we also have the change in angular momentum, also known as I bar alpha. And this should really have a bar also. So the first thing we're going to do is sum the forces that are detailed in the in the free body diagram and set them equal to the forces in the mass acceleration diagram. And in this case, we've set our coordinate axes to down is positive y, and then to the right is positive x. So in this case, our forces will be mg minus t equals ma. Okay, so we've got one equation, and we want to find one more equation so that we can combine them and find the acceleration. So we're going to do that by summing the moments that are detailed on each diagram and setting them equal to each other. So that's the moment about the center from the free body diagram equals moment detailed on the mass acceleration diagram. And this is basically going to be the moment caused by the tension. That's the only moment that is going to be caused, and that would be the tension times the moment arm to the center, which would be little r, and that will be equal to the change in angular momentum, which would be I bar alpha. Okay, now I bar, in this case, in a perfect world, with the perfect yo-yo, would be equal to 1/2 of the mass times big R, the entire radius, squared. Okay, now remember, the acceleration is equal to alpha times little r. So our alpha is going to be equal to alpha, or acceleration divided by r. Okay, now what we can do is solve for t, and that'll get rid of this r, square this. Now remember that r is equal to 2r. Or let me rephrase that. Big R is equal to 2 times little r. So big R, meaning the outer radius, is twice that of the inner radius. So we can actually set big R to 2R. Now if we were to square that whole thing, that would be 4R squared. Now these R's cancel out. Okay, so we have, this would be equal to 2MA. Now I'm running out of room over here. Actually, I can move up. So now at this point, we've got this equation, which is T equals 2MA, and we can plug it into this equation. So, and keep in mind this is A bar. Same thing. Okay, so from here we're going to go to, actually let's go up here. So T equals mg minus ma, and then bring our 2ma, which is equal to T, so 2ma equals mg minus ma. We can cancel out all the m's. So we're going to have 2a plus a equals g. We combine these, we get 3a, and then divide by 3, so we have a is equal to 1/3 g. And that will be our acceleration. So something significant to conclude from this video is that the acceleration is not dependent on the mass. It's dependent on little r and big R. And depending on those numbers, this coefficient will change. Thank you for watching.